Good morning, grade 10s. How are you guys doing today? Uh, Welcome to this physics lesson. Today we are looking at heat capacity, thermal capacity. Those terms are interchangeable. Uh, this is a new concept again for you guys, so I really want you guys to pay attention. The idea itself is not necessarily new. It's something that you guys already know about. But by the end of this lesson, we should be able to define the term heat capacity to explain what we mean by heat capacity. You'll find that as you are researching about this concept, you'll find terms or you'll find the concept of specific heat capacity also coming up. That's something that we're going to do in the next lesson. But prior to that, we need to know what heat capacity is. We need to relate the rise in temperature of a body to an increase in internal energy, the energy of the particles that are possessed by that particular body. And for us to do this, we use an equation. This equation, recall and use the equation C is equals to Q over delta T, where those letters you get to know that C in fact stands for heat capacity, delta T change in temperature, and the Q is effectively the amount of energy that would have been placed or the amount of heat that would have been applied to a body. To say if I apply this much amount of heat to a body, what is the temperature change going to be? And that then in turn tells me what the heat capacity of that object is. Okay, so just look at these objectives. If you want to look up at what heat capacity is, just look it up before we continue. Okay guys, so you will notice that this concept of heat capacity it's a very simple concept, because all it's doing is that it's now explaining to you basic everyday life concepts that you meet, where you know that when energy or heat energy is applied to an object, its temperature is obviously going to rise. Its temperature is obviously going to rise. But the temperatures of different objects rise at different rates. Okay? They rise at different rates. So observe like the image that is now here on the screen, where you have the sun, its heat, the heat energy from the sun is going onto the sand. At the same time, it's going onto the water, right? But you will find that the temperature of the water and that of the sand will not increase at the same rate. They will increase at different rates. Okay? So the sand, the temperature of the sand, because of the nature of the material, right? The material, the sand itself, silicon oxide or silicon dioxide, it's easier for the sand to gain heat as opposed to the water in the ocean. So you will find that when we say heat capacity, and we say heat capacity of an object, I'm going to read from here, the definition of heat capacity. The heat required to raise the temperature of an object by 1 Kelvin. The temperature or the heat actually required to raise the temperature of an object. Imagine an object, whether it's a metal spoon, a plastic spoon, whether it's sand, whether it's a brick, whatever object you might try to think of, the amount of heat that is required to raise the temperature of that object by 1 Kelvin. And remember that 1 Kelvin is equivalent to 1 degree Celsius. So then don't end up saying, what is 1 Kelvin? Who is Kelvin? Where does it stay? No, 1 Kelvin, remember we talk about an absolute scale, right? Absolute zero, the temperature scale where we use kelvins because those ones are more accurate. So in physics and in chemistry, we measure our temperatures using kelvins, not degrees Celsius. So if you have water and you want to find how much heat is applied and heat is measured in, I hope you guys know what the unit for heat is. You can just pause the video for few seconds just to go and look what the unit for heat is, right? Pause the video. Okay. So you'll find that the unit for heat is measured in joules or kilojoules. And we'll say that the heat capacity of an object is dependent on certain factors. The mass of the object. The mass of the object. Obviously, you know that it will take less heat for you to raise the temperature. Let's say you have a small cup of water and you want to heat it up and you want to raise its temperature. The amount of heat required for you to raise its temperature by 1 degree or 10 degrees is much less than the amount of water you would have to apply to a drum. Compare a cup of water, a drum of water, both full, right? You will obviously need more heat to raise the temperature of the water in the drum. So also you can use different substances. Let's say if we had water and we had oil. Oil and water, they have different densities, yes? We know that oil and water have different densities. The materials themselves are obviously different. The components, the chemical composition is different. So the amount of heat required to raise 1 kilogram of water, that's exactly 1 kilogram. 1 kilogram is exactly the same as 1 liter. So don't get confused there as well. So the amount of heat required to raise 1 liter of water by 1 degree Celsius is not the same as the amount of heat required to raise the temperature of 1 liter of oil by 1 degree Celsius. Okay? So if you can read the information written here, it tells you, it shows you that effectively for you to heat oil to 60 degrees Celsius, right, you actually use half of the amount of heat. Let's read the whole thing as it is. Identical volumes of water and oil heated for 1 minute at the same temperature. The oil will heat to 60 degrees Celsius, whereas the water heats to 30 degrees Celsius. So which means the same amount of heat, okay, produces twice the temperature rise in oil than in the water, which is the same as saying half of the energy that is required to raise water to a certain temperature doubles the temperature rise in oil. Okay? So you'll observe that with heat capacity, it's going to be different from substance to substance. That's the main thing we want to highlight in this lesson. To say different substances have different heat capacities. Right? Different substances have different heat capacities. This means that water has twice the capacity to absorb and store heat energy than oil, right? In reference to this example. So if you want something that you can use that is slow on absorbing water, on absorbing heat, you use water instead of oil. I think you can just see it. When you put oil on cooking oil in a pan, its temperature is going to rise much faster than that of water. Okay? So now, continuing, we find that heat capacity on an object is directly proportional to its mass, which means that as you increase the mass, you also increase the heat capacity. Heat capacity also depends on the type of the material. This is what we've just explained. Then heat capacity is calculated using this formula. Heat energy applied divided by temperature rise. Heat energy is represented by the letter Q. Heat energy will be in joules or in kilojoules. Heat energy will be in joules or kilojoules. Whereas temperature rise, delta T. Delta T just means change in temperature. Change in temperature represented by final temperature minus initial temperature. Okay? Remember last time we talked about change in momentum, delta what? Was it delta V? Change in momentum, where you will have final momentum minus initial momentum. When you want to talk about final velocity minus initial velocity, the delta just means change. Okay? So, this is the formula that you use. So say, if I want to calculate heat capacity C, I must know the amount of energy, heat energy that was applied to a substance. Okay? Then you represent it using the letter Q or the number, amount of joules. Then you divide that by the change in the temperature. So you're going to measure the temperature of a substance first. So if you were using, let's say this is this water, what you would need to do would be to measure the temperature of the water first, and you say, okay, the temperature of the water is maybe 30 degrees Celsius or 25 degrees Celsius at the beginning of the experiment. After applying 50,000 joules or 5,000 kilojoules of heat, it changed from 25 degrees Celsius to 55 degrees Celsius. Now you have your heat applied and your heat energy applied, and you have the temperature change as well. Let's look at a simple example here. So in this example, we are given an electric pot with the power of 5.6 kilowatts. If it takes it 4 minutes to heat water from 20 degrees Celsius to 60 degrees Celsius, calculate the heat capacity of the electric pot. Okay, so what you have to do here, know that we want to look for heat energy, and this is power, right? This is power, which means power is in kilowatts. Kilowatts are the same as joules per second. I hope you remember the formula from the topic on power. That's joules per second. So if you want to find the joules, you now have to remove the seconds, which means you change the 4 minutes. That's where you get the 240 from. I know someone is going to ask, where did the 240 come from? Where did the 5,600 come from? 5.6 kilowatts is the same as saying 5,600 or 5.6 joules, 5.6 kilojoules per second, right? So that's the same as saying 5,600 joules per second. Then you divide by 240 because 4 minutes has 240 seconds in it. So you divide, actually you multiply. So it's for you to cancel out the seconds, because that's J over S multiplied by S. If you have J divided by S multiplied by S, the S and the S are going to cancel out. Okay, cool. Then if you say 5.6 multiplied by 240, then you get 1,344,000 joules. Yes, right. Now what you want to do is you also want to find the temperature, the change in temperature. So you will say final temperature, which is 60 degrees Celsius, less the initial temperature, which is 20 degrees Celsius. But again, remember, we said when we are doing our calculations in physics, we use kelvins. So on the Kelvin scale, what is 20 degrees Celsius? Remember, the Kelvin scale starts from 273. 0 degrees Celsius is equivalent to 273 degrees, to 273 kelvins. I hope you didn't get confused, just wondering where did the 333 come from. You must remember always that 0 degrees Celsius is 273 kelvins. Okay? So 60 degrees Celsius, you just add it to 273, it becomes 333 kelvins. I know I'm rushing a bit, but you guys can always pause this and go back. Even now, I can even encourage you to pause the video, go back, listen again and again and again, and come back to where I am right now. Okay, so that's 333 kelvins less minus 293 kelvins, which is equal to 40 kelvins. And not 40 kelvins, not as in NOTE. Observe that 40 kelvins is the same as 40 degrees Celsius, right? It's just more accurate. Don't worry about it. So now we are now replacing these values into our equation, right? Into our formula. Our formula says heat capacity is equal to Q over delta T. We know the amount of energy that was applied, 1,344,000 joules. We know the temperature change, 40 kelvins. Therefore, we divide the two, and we get 33,600 joules per Kelvin. That's the heat capacity. So the unit for heat capacity also is going to be joules per Kelvin. Yes, it's going to be joules per Kelvin. Right, so that's all, guys, that I have for you in this video. I hope you enjoyed the video. Always watch the videos don't just rush through them. Watch the videos so as to avoid you coming into the actual lesson confused and stuff. Thank you guys. See you in the lesson proper.